I'm Ben with G2 Engineering, and in this video I want to talk to you about four-legged kinematic mounts. Now, if you try to Google four-legged kinematic mounts, you'll mostly get back results explaining why such a mount cannot be built. And the reason most often given is that, hey, did you ever see a four-legged restaurant table that doesn't rock? Which is a fair question. So before we can talk about four-legged kinematic mounts, we need to talk about restaurant tables. Voila. Now, as I'm sure you know, a three-legged restaurant table is indeed always stable, even if the floor of the restaurant is uneven. But a four-legged restaurant table is not so stable. So based on that, traditional kinematic mounts have always been built using three mating elements, in this case each element being a sphere inside a V-groove, and are always stable, of course. But here's the thing, in real life most of the objects we deal with are rectangular in shape, like optical breadboards or cars, for example, and so it would be very convenient to have a kinematic mount that has four mating elements instead of only three. But what about the restaurant table? So to reconcile this, we need to understand the difference between a three-legged restaurant table and a three-element kinematic mount. See, with a restaurant table, when we say that it is stable and it doesn't rock, we still implicitly assume that it is free to move in the plane of the floor. So it can translate in X and Y, and it can rotate around the Z axis. So in fact, it's only really constrained in 3 degrees of freedom. And so when we try to place it over 4 legs, we introduce at least 4 constraints, and therefore we over-constrain it, and therefore it rocks. But with a full kinematic mount, it is completely fixed in space, and so it is constrained in all 6 degrees of freedom. And so it should be possible to have 4 mating elements as long as they add up to 6 kinematic constraints. Now, to see how this is done, we're going to have to replace our restaurant table with a different top plate. And what we've done, we've attached a cone to it and 3 spheres. So we're forming 1 cone to sphere mating element, which we'll call the pivot, and 3 sphere to sphere mating elements. And as I apply the cone to sphere, the pivot mating element, I constrain the top plate in 3 translational degrees of freedom, so it cannot move in X, Y, or Z. But what it can do is it can rotate in the plane, it can tip up and down, and it can tilt. These last degrees of freedom get constrained simultaneously as I lower the plate onto the optical table and engage the 3 sphere-to-sphere mating elements, and voila, a 4-legged kinematic mount. Now, the secret, of course, is in the position of these spheres. What we require is that the set of torque vectors, as applied by these 3 mating elements around the pivot points, be linearly independent, and that the force vectors in each of these mating elements have a Z component significant enough to support the load. But once these conditions are met, we have 3, 4, 5, 6 kinematic constraints for 6 degrees of freedom and a full kinematic mount, which I can demonstrate by evening out the flow of our restaurant, reapplying the mount, and seeing how it finds a new, unique, different kinematic solution. So the geometry I just demonstrated is good for illustrating the feasibility of 4-legged kinematic mounts. But this is not the only possible geometry. We can get a more symmetrical geometry. by using two sphere and groove mating elements and two sphere to sphere mating elements, again for a total of 6 kinematic constraints. As I engage the two sphere and groove mating elements, I constrain a total of 4 degrees of freedom for the top plate, so it can only rotate in the plane or tip up and down. As before, the last 2 degrees of freedom get constrained simultaneously as I engage the two sphere to sphere mating elements, and I get a full kinematic mount. Again, I can demonstrate the kinematic mount by evening out the flow of our restaurant, reapplying the mount and watching it find a new, unique, different kinematic solution. So what I've done here is demonstrate the concepts and geometries of four-legged kinematic mounts. In order to apply these principles towards a ruggedized high load capacity real-world kinematic product, we need to employ the same techniques we use with the three-legged kinematic mounts. That is, we need to look into the mating elements and eliminate any point contacts in favor of line contacts, increasing the load capacity by 2 orders of magnitude. And to see how we do this, please tune into the video called Three-Legged Kinematic Mounts, also on our website. So, thanks again very much for your time, and I'm Ben with G2 Engineering.